Hello, everyone. My name is Devendra Kapatia, and I'm the manager of Calculus and Algebra at Wolfram. It's a great pleasure for me to speak about what's new in Calculus and Algebra at Wolfram with you today. Now, just want to say a few things before I begin the talk itself. The first point is that we have had another release recently, 12.3, and we've got one coming up, 13.0. I'm sure you all want to hear about 13.0 rather than 12.3. So most of my talk is going to be about 13.2 and not 12.3. The second point is that the work I'm presenting today is the work of a very large group of developers all over the world. And I realize that what I'm speaking about is really their work. So please, remember that I'm really speaking on their behalf, and it's a pleasure to acknowledge all their help. One last thing, this is the first of a series of talks this afternoon about Calculus and Algebra. So please support us by attending as many talks as possible this afternoon and giving us your support for this series of talks. So let me begin now then with a brief overview of the talk, the plan for talk. So in this talk, I will discuss new features related to the following areas. The first one is calculus itself, the core area that we have always had. And for calculus, we have symbolic integration, differential equations, a new function poles function, bilateral Z transforms, lots of stuff. Then I'll go into algebra, where we'll talk about both polynomial and linear algebra. There are improvements over there as well. I'll go into special functions and talk about the Fox H function and the new Fox HReduce function, the Coulomb functions, and new interval support for special functions. Now, for us as a team, documentation is always a very important thing. So we've been working on documentation for special functions and elementary functions. And it's a great pleasure to actually talk to you about that vast improvement that we have for this release. For us, another point is if you want to benchmark what we do, you want to figure out how good are we? How good are we with respect to our competitors? And I'll talk about a very large benchmarking project that's just come to an end recently. So I hope that you'll enjoy listening to this benchmarking part as well. And one last thing is that we always are trying to do new online courses. We have a new course coming up. I'll talk about that as well towards the end of the talk. So let's begin with symbolic integration. Now, the integrate function uses something called a Risch algorithm for integration, for in-depth integration. And one of the things over here is that we have always had a good Risch algorithm implementation, but the algebraic case has been very difficult. And to understand why that's the case, remember that this was done around 1960 with Robert Risch, and Risch was actually stuck at the end in the algebraic case, and he wrote to Goro Shimura, and Goro Shimura gave him a hint as to how to finish up, and Goro Shimura's work was actually used for the proof of the Fermat's last theorem. So no wonder that there is, to our best of our knowledge, no complete implementation of this functionality, which is also practically useful. So version 13 has heuristic methods for algebraic integration. And there are two examples over here. The first one has one in which you actually only have like a half-line answer in 13.0, but in the earlier release, you actually had a huge number of elliptic integrals. If you're not careful, they would fall off your screen, and if you didn't catch them, they just fall on the floor. And the other example over here is this integral, which where it's for the first time in 13.0. It's a beautiful answer, entirely logarithmic, so to speak, but it's a wonderful answer. So this is very nice work done by Sam Blake, and hopefully this will improve the quality and scope of integrate in this area. I'm sure it will. Going on now to definite integration. So over a number of years, we've had people kind of, telling us that we need to improve our definite integration in the following class. In the class where you have kind of trig exponential integrals, and these integrals have always given kind of not so satisfactory answers. So what we have done now is to implement a complex contour integration based method for this class of integrals. And so here's an example which would give essentially a wrong answer in the earlier release, but now it does a beautiful job of giving back just the right answer. You compare with n integrate, and you get the agreement quite nicely. So probably over the last 20 years, we've had, the whole suite of examples, 25 of them, some from Nobel Prize winners, some from near Nobel Prize winners, and they all tell us, please improve the area. We've done it now. It seems simple at the end, but in fact, it's pretty much amazing that it works inside our integrate machinery. So that's work done by partly, but Danny Lichtblau gets credit for this work in the end. So thank you, Danny. And now the question before us is, if you have contour integration, like in the earlier case, it was simple because you could reduce to a rational function. What happens for more general contour integration? Now, I have privately developed a contour integration function, which I've tested against the most popular textbooks of complex analysis in the market, and they work nicely. But what we need was a dedicated function which would compute for us the poles of any meromorphic function. We have it now, function poles. And here's an example of the gamma function. You see the gamma function over here. And you see over here, there are 5 poles in the unit disk. You compute the 5 poles, 1, 2, 3, 4, 5, apply residue theorem, and lo and behold, you get an answer which agrees with an integrate. So hope is that in the upcoming releases, we'll actually have a wonderful kind of, implementation of complex contour integration in Mathematica. So going on to differential equations, we now have support for vector variables. So the point is that people have always told us, why can't you let us have matrices inside DSolve? Well, you can now. So here's the simplest possible example on Earth. Y prime x equal to z of x, z prime x equal to minus y prime x. The answer is sine and cosine, but now you can do it in this beautiful matrix notation and get back the answer. So that's another win for us in this release. Use vector variables, use matrices, you're just fine. Only tell us, okay, this is a 2 vector, this is a 3 vector, whatever, and then we'll do it for you. Now, once you have this kind of machinery for vector variables, it's nice to understand, very easy to understand the next improvement, which is graph reduction. So in early release, we had trouble with these so-called coupled systems. The problem was that we just couldn't see the relationship between them, and people complained to us basically on Stack Exchange, etc. And we now have a nice way of doing this. So here's an example of a 4x4 system. The first equation depends only on the first variable. You can solve it, e raised to sine t, plug it back over there, use that solution, and then solve the whole system. So this kind of thing didn't work so well in early releases. We've done it now, and here's the beautiful answer from DSolve for this example in the matrix notation. So we have the improvements for DSolve and also for RSolve in version 13. And if you want to know more about them, visit our office hour tomorrow. Aram Manaselian, with this very elegant work, has actually worked hard on this. So please meet him and discuss your office hour kind of questions about DSolve. Okay, then moving on to partial differential equations. So we have a new function called complete integral, which actually gives solutions with arbitrary constants for a first order PD. Now, when you solve a first order PD, you typically expect to have arbitrary functions. Think about it, if you got a function of 2 variables, then if you put the partial derivative equal to 0, then any function of with y equals 0, then any function of x will satisfy the equation. So in fact, you usually have arbitrary functions, but now you can use arbitrary constants. And this solution depends upon n arbitrary constants for a PD in n variables. So here's an example of the so-called Clairaut equation. And the Clairaut equation looks dreadfully complicated, but the solution given by this new function is wonderfully simple. It's a bit like projective and projective geometry, where you actually see that the dual answer is very, very simple. So starting from this solution depends upon 2 parameters, C1 and C2. You can then build an envelope solution. You can take a 1 parameter family of planes by setting C2 equal to -1. You can do the envelope construction and get a nice nonlinear solution. So the earlier solution was just a 1 parameter family of planes, and now you get this envelope solution, which is actually a quadratic solution. You can check it's a solution and you can plot it. And what you see over here is that this is the complete integral. It kind of glides over the envelope, and you actually see the beautiful solution of the envelope coming up. So to know more about this, we have a talk by Unal Goktas this afternoon about PDs. He's worked very hard on them. Do attend Unal's talk. It should be very, very nice. He'll talk about version 12.3, the monograph, as well as the complete integral 13.0. Okay, then moving on to further calculus. So we had the bilateral Laplace transform in version 12.3, and now we have a so-called bilateral Z transform, which is given by an infinite sum, a doubly infinite sum, and the inverse is given by a contour integral. But now we become experts in contour integration, no problem at all. So we have two new functions, a bilateral Z transform and the inverse bilateral Z transform, which provide this functionality in version 13.0. So here's a simple example. You have an exponential decaying sequence on both the sides. The Z transform works on one side, generating function on the other side, and then you actually get the whole sequence. You find the Z transform. You see there's a region of convergence over here. Very important. Here's a plot. It's an annulus. You do a contour integration and you get back the sequence. So this is new functionality in version 13.0, the bilateral Z transforms. And just to point out to you that the request for this came to us in 1999, and the developer who worked on this told me that he was probably in elementary school when this suggestion came in, and many years later, he actually developed a function. So well done, Haraj. Nice job with the bilateral Z transform. It's going to be very, very useful. Okay, so then I move on to algebra, and we have a nice new function called polynomial sum of squares, which actually relies on our optimization capabilities to check if a given polynomial is a sum of squares or not. So here is a polynomial. Question is it a sum of squares or not? If it is, then it gives back this list, this function, and in this case it does. You can check that the answer is correct. You just dot the answer with itself and check the solution is correct, and you can check that the function is non-negative by doing a plot as well. So polynomial sum of squares list, that's one of the largest names in the system. I'm not sure it's a record, but probably very, very close to record. So, we have a very nice implementation of this. It relies on optimization. So it's not going to be 100% correct in the sense that you cannot guarantee it's going to work, but when it works, of course, it will give you the correct answer. So Adam Stresbonsky is the expert on this, and he's done a beautiful job. We have three new linear algebra functions. They are very closely related to inverse. Adjugate got promoted from the function repository, did a good job over there. Well done, Adjugate. You're now in 13.0. And they've got two new functions, the core nilpotent decomposition and Drazin inverse. You see what happens when a matrix is singular, then it has zero eigenvalues. So that's the kind of nilpotent part, and the rest is the core part. We throw away the nilpotent part and you get the Drazin inverse on inversion. And here you see that we have a singular system of differential equations, ay prime plus by equals 0, and you can find the solution using the Drazin inverse. Basically, the determinant over here is 0. So it's a singular system. You can see over the determinant is 0. But if you do a plus b, the determinant is no longer 0. So then you can use Drazin inverse to find the solution, and you can check the answer DSolve value. You might wonder why. How did it know? Well, we actually have this algorithm inside DSolve for a long, long time. So these functions already inside DSolve. All we have done is to export them to the system. Okay, so Drazin inverse is a very useful function. It's a very difficult function. The developer told me that even MATLAB doesn't have it, probably because it's so hard to work in the machine number case. But well done, Jan Mangeldan and Knarek Hovhannisyan, who worked on this. Okay, going on to special functions, we have, you see, we had FoxH in 12.3, and FoxH is a huge function, includes lots of special functions in it. And the question is, can we then find out how each function relates to FoxH? So what FoxH reduce does is it actually reduces any function which it can to a FoxH expression. So here's the inactive FoxH, which you get back. You activate it and you get back the original function sign in this case. And it works on a huge number of cases. So here's the exponential function. It's FoxH, polynomial exponential, it's FoxH, trig, hyperbolics, all kinds of stuff just works beautifully with the FoxH function. Bessel, Airy, hypergeometric, Meiji, and the Mittag-Leffler function, which you see over here, which actually is the analog of the exponential function for fractional differential equations. So when you solve a differential equation with constant coefficients, you get exponentials. when you solve a fractional differential equation with constant coefficients, you get the Mittag-Leffler function. So Fox HReduce is a wonderful new function, 13.0. There's a talk by Tigran Ishkanian this afternoon, which you should definitely attend. He's done a great job of putting the talk together. I saw the talk. It's very friendly, very informal, very chatty. Tigran is a great speaker, so please come and encourage this young mathematician who's been working on this function. Okay, on to the Coulomb functions. So you might think Fox-H was enough for us, but we still had a little bit left over. So we got these Coulomb functions in version 13, and there are 4 of them. There's Coulomb F, Coulomb G, Coulomb H1, Coulomb H2, and they are all solutions of this second order ODE. So if you have a second order ODE, then in fact you should only have 2 independent solutions. So they are Coulomb F and Coulomb G. This one is the regular solution. This one is the irregular solution. And the remaining 2 are complex linear combinations of them. They're usually called Coulomb H plus and Coulomb H minus, but we call them Coulomb H1 and Coulomb H2. Okay, so here is a plot which shows the first 3 Coulomb functions, Coulomb F, Coulomb G, and Coulomb H1, absolute value. And you see there's a plot over here, which is actually from the DLMF, the digital library. And as Stephen mentioned yesterday, this is occasion to celebrate because we now have covered everything in the classic book by Abraham Stegen, which was written somewhere in the 1960s or 1970s and is now completely caught by us. If there's a bit left over, we'll let you do it yourselves by defining a user-defined special function in the near future. Okay, and one last thing on the special function side. So we have support for these so-called centered intervals. So in version 3, we introduced this so-called interval function, which lets you do arithmetic with real intervals. And now in version 13, we have centered interval, which does not just real arithmetic with intervals, but also complex arithmetic. And I really like the typesetting over here. So you see, you have a real interval over here with center 2 and radius 1 over 100. And you have a complex interval with center that and kind of radius 1 plus I over 20. So you get a real interval back over here. Look at the visual, a complex interval over there. You can add them, you can multiply them, you can do what you like with them. And in fact, if you have a function like log or sine and you apply it to a centered interval, the answer will have, it will define rectangle which contains the original function. So it kind of gives nice bounds. They may not be sharp, but they are pretty useful. So this works for 103 elementary functions. It's a huge area. The person who knows best about it is Adam Strisbonsky. He'll give a talk this afternoon just after me, and do attend his talk. Adam is an expert. Listen to him talk about optimization and centered intervals and all that kind of stuff. Okay, so now we move on to documentation. And like I said, we have always tried to do documentation for every release. So for version 12.3, we added documentation example function properties to 110 functions. Now we added another 140, and together we have function property examples on 250 pages. Also, there are some beautiful new examples for linear algebra, things like eigensystem, eigenvalues, etc. And the plan is now to improve that same area for integral transforms in the near future. So the people who worked on this, Anush Sargasyan and Klarik Khovanesyan and Itai Segev, need my thanks, and thank you very much, all 3 of you. There's a talk by Itai Segev where he'll talk about this functionality in great detail, and also other things in the kind of college mathematics area for calculus, etc. So do attend Itai's talk. It should be a very nice talk later this afternoon. Okay, so now I'm getting close to the finish of my talk. I go to benchmarking. So we have finished a very large benchmarking project for this release. So around 3 years ago, we started the benchmark project. What happens is Roger Germanson says, okay, let's do this benchmark. Then some kind soul like one of our interns or Michael Trott typically will say, here's a large benchmark for you. Henry Collins run it. He sent it to me, and then I'll check it, do a cursory check. I can't check them by hand, obviously. And then over a number of years, we have built this huge benchmark, which as of today has got 18,387,711 problems for 46 functions. So here's the word cloud, which shows them all. And the winner over here is integrate, of course. And there are lots of other functions which are doing pretty well in a number of problems. But when I get one of these reports, I can also tell Henry, oh, give me a report for so-and-so function with what works, what doesn't work, etc. This is a real feat of notebook programming, parallel computation, database manipulation, and well done, Henry. This project is now more or less done. And one last thing. And the last point is that we always try and do one new course every release or so. And for this time, we have a course on differential equations. So this course has been worked on for a couple of years now, began with Aaron Crenshaw, then Luke Titus stepped in to help out over here, and Luke has done a great job with this course. It's got lessons, problem sessions, exercise, quiz, and a final. It's a beautiful course. It should be available very soon. I just want to thank Luke for all his great work on this particular course. And for me, I'm only thinking of next year. So I have a course on elementary algebra and multivariate calculus planned for 2022, which I'll probably record myself at the second one. The first one is Arben Kalziki, who recorded the first one. So if you like education, I'm doing a meetup on Friday. Do come along for it and participate in high school mathematics, which I think is the most important topic for us going forward. So do come and enjoy the discussion on education at the high school level. But I think these courses are now turning out to be wonderful for us. I get letters from all over the world telling me how people are enjoying the course. People in the faraway Himalayas, etc., write to me, and I feel we are doing a good job for society and for ourselves. Okay, so maybe it's time for me to stop and say thank you. Thank you to you for coming here today. Thank you to our wonderful team, which always helps me. Thank you to everyone else in the company who supports us. It's been a difficult period. I'm in my office right now. You see the black blinds behind me are our office blinds, but we have worked remotely and still done almost as much or even more than what we had expected to do. So credit goes to the people who work on this relentlessly, tirelessly, and without complaint. So with all that, I'll stop over here and take a few questions, but it's been a great pleasure to talk to you. And I do hope you'll attend all the remaining talks this afternoon. They should all be great. So I guess we have time for maybe 4 or 5 questions. I see lots of questions coming up. That's a great thing happening. I usually don't have so many questions for my talks, but let's see what's happening. So questions, are the calculus course from you based on the University of Illinois calculus courses that use Mathematica? Not exactly. I think the book that we follow, to be honest, is Stewart's Calculus, which is very universal. Although I feel the U of I does a really good job with those calculuses. I know the person looks after them. Okay, so but I think they are very inspirational. We don't exactly follow them, but we might do that in the future. So next question, is it possible to find the Risch method? Possible for the Risch method to be fully implemented at some point? Probably next 5-10 years. Sotiris, I'm not sure. Okay, I hope you're all having sound now. Okay, so do you get proofs for integration methods? Not right now, you might in future. Are the 2D support? Yes, they are. Okay, how is centered interval relate to around? Good question. Centered interval is very kind of, very much accurate. It doesn't use statistics. Basically, around is much more statistical, but to understand that, go to Adam's talk. He knows a lot more than I do. But roughly speaking, around is statistical, and centered interval is actually, very accurate. Okay, so thank you, Mads, for your comment. And I really appreciate all your support. I really need to finish up so other people can come. And yeah, there are Dan Hooper, our excellent IT manager, reminded me that I got a few questions. Sure, I am. And I appreciate all your support. Do come to us. Okay, Eric Weisson says the longest one is $definite remote batch submit environment. Okay, Eric knows everything about Wolfram language, so I believe you, Eric. You are absolutely right over here. So with those words, I think I really should start stopping now because we are getting close to our finish time. But once again, thank you very much for all your work, and I'll finish up over here. Maybe if you have a couple of questions, you can wait for a minute. But thank you, everyone, and well done, team, again.